Hey there, 8th grade. In this next video, we'll look at how to graph logarithmic functions. Okay, so we're going to start out with identifying that a logarithmic function is the inverse of an exponential function. And just like we learned how to graph exponential functions starting with the parent function, we'll do the same thing with logarithmic functions. The parent function for a logarithmic is f of x equals log base 10 of x. Okay, so all of our graphs are going to be based on this basic format right here. Before we jump into how to graph a logarithmic function, I want you to consider these two graphs. We'll look at the graph for the parent logarithmic function, and then we're going to look at the graph for a parent function for an exponential f of x equals 10 to the x power. And we'll use our graphing calculator to look at these. So I'm going to start by graphing on my calculator f of x equals 10 to the x power. And you should know what the basic shape of that is going to look like based on what you know about exponential growth. Okay, so this is what that second graph looks like. So we'll just really quick do a rough sketch on our paper of that. Again, it has a horizontal asymptote at y equals 0 and an increasing graph. It's going to have a y-intercept at 0, 1 because if x is 0, 10 to the 0 is positive 1. So that's what this graph looks like. The graph of a logarithmic function is going to be the inverse of this. Okay, so that's what this graph over here is going to be. And we didn't really talk about this in the last unit a lot when we did inverses, but anytime you want to get the inverse of a graph, you simply need to reflect it over the line y equals x. So I'm going to draw that line really quick in dashed format so you can see what it looks like. Y equals x is just a diagonal line with a slope of positive 1 that goes through the origin. So if you imagine taking this blue graph here and just flipping it over this purple line, you're going to get the graph of f of x equals log base 10 of x. And we can see that using our calculator here. So here's my first graph, okay, the exponential function. And now if I graph f of x equals log base 10 of x, you'll see that again, that purple line here, this blue graph flipped over to get the red. Okay, so that's what a logarithmic function looks like. It looks sort of like an exponential, but it's going to be the inverse of an exponential function. Okay, so this graph is increasing. It has an x-intercept at 1, 0, as opposed to a y-intercept at 0, 1. And this graph actually is going to have a vertical asymptote as opposed to a horizontal asymptote. So it's going to approach the y-axis here. Now on most calculators, with the exceptions of the ones you have, you can only graph base 10 logarithms. So that's how we're going to learn to do our graphing, is based on base 10. And because of that, we will need to use the inverse exponential function whenever we're setting up our t-charts. So we're going to start with the inverse exponential function when we're setting up our t-charts. And then after that, we'll invert our x and y values from our tables to get the graph of the actual logarithmic function. So let's look at how that looks down here on example 1. Okay, I'm asking you to graph f of x equals the log base 2 of x. Well, I'm going to start out by thinking about what the table for f of x equals 2 to the x power would look like. Again, because that's the inverse of this logarithmic function. So this is something we've already done. To graph this exponential function, I would set up my table. I would choose values based on my h value, which is 0. So I would choose -2, -1, 0, 1, and 2. And when I put in these x values for x, I get 2 to the -2 power, which is 1/4. 2 to the -1 power, which is 1/2. 2 to the 0 is 1. 2 to the first is 2, and 2 squared is 4. So these are the values of this exponential function. So now, if I flip these x and y values, because that's what, again, it means to be an inverse function, is when x and y are switched, I'm going to get my table of values for my logarithmic function. F of x equals log base 2 of x. And so these values that I'm going to put here in red are actually what I'm going to graph. So my x value, my y values are now -2, -1, 0, 1, and 2, and my x values are 1/4, 1/2, 1, 2, and 4. Okay, An exponential function's inverse also flips the horizontal asymptote. Normally this would be a horizontal asymptote at y equals 0, but now that we're doing the inverse, it's actually going to be a vertical asymptote, so it's going to go straight up and down on x equals 0. So our asymptote is going to be right here when we go to graph this. Okay, so I'll plot these values: 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, and 4, 2. And so this logarithmic function is going to look like this. Let's identify some characteristics. We already did the vertical asymptote x equals 0. Just like everything else flips x and y values, the domain and the range are also going to be inverted. For all our exponential functions, the domain was always all reals. Well, for logarithmic functions, it's going to be the range that is all reals. Okay, this graph goes forever downwards and forever upwards. It's growing, so that's the range. The domain, however, is restricted based on this vertical asymptote. All of our values here are graphed to the right of this dashed line, so my domain values are all the x values that are greater than 0. So that would be the domain. Okay, let's look at the end behavior for this one. So you'll notice as the y values increase, as the y values get larger, what's happening to x? X is also getting larger. So as x grows, or grows to infinity, so does y. As the y values get smaller, so as the graph goes downwards, what's happening to x? X is getting closer and closer to 0. So x approaches 0. The last thing we'll look at is the x-intercept. And the x-intercept is just when the y value is 0. We have that in the table right here. This has an x-intercept of 1, 0. All right, let's do the same thing for number 2. We'll graph the function f of x equals log base 1/3 of x. And again, we'll start out by thinking of the inverse exponential graph, and that would be f of x equals 1/3 to the x power. So let's look at this table of values. Again, our h value is 0, so we'll do -2, -1, 0, 1, and 2. And when we put in our exponents here, 1/3 to the -2 power is actually going to be 3 to the second, so that would be 9. 1/3 to the -1 is the same as 3 to the first, so that's 3. Our 0 power here will give us 1. 1/3 to the first is just 1/3, and 1/3 squared is 1/9. So now to get our table for our actual logarithmic, we're going to flip these and do the inverse. So our table for f of x equals log base 1/3 of x is going to have the y values at -2, -1, 0, 1, and 2, and the x values will be 9, 3, 1, 1/3, and 1/9. Okay, so same thing for the asymptote. This would normally have this one here would have a horizontal asymptote at y equals 0. So now our vertical asymptote is x equals 0. We have 9, -2, 3, -1, 1, 0, 1/3, 1, and 1/9, 2. So our graph looks like this. Again, our vertical asymptote is x equals 0. Our range is always going to be all reals for these. The domain, same as the last time, is all the x values that are greater than 0. They're all to the right of our vertical asymptote. Our end behavior, so as y gets larger, y is getting larger as this graph goes upward. What's happening to x? X is getting closer to 0 as y gets larger. Okay, so this is how we fill in our end behavior. As y gets smaller, okay, so as you decrease, what happens to x? X gets larger. Okay, x grows to infinity. The x-intercept, same as the last one, is going to be 1, 0. Okay, now let's look at a more complex logarithmic function, and that's going to be the function f of x equals log base 10 of x minus h, that quantity, plus k. So this should look a little bit familiar to you, the h and the k, because these are the values, these are the variables we always use when describing transformations of graphs. Okay, so the same rules apply as did with exponentials, as did with quadratics, as did with absolute values. This h value, the value next to x inside the parentheses, is the horizontal shift. Okay, it's the horizontal shift. So if it's a positive, it's actually going to shift the graph left. And if it's a negative you see here, it's actually going to shift the graph to the right. Okay, this k value here, that is the vertical shift. A positive there is going to shift the graph up, and a negative there will shift the graph down. So now we'll graph some functions that have these transformations in here. Okay, so f of x equals log base 4 of x minus 1. Okay, I'm going to start out by thinking of what the t-chart for f of x equals just log base 4 of x would be. Okay, that's going to be how I start out my t-chart. Now, I'm going to go ahead and skip a step from what we did in 1 and 2 here. Okay, so we know that this t-chart here is going to be the inverse of the t-chart for the function f of x equals 4 to the x power. Okay, so let's consider what I just wrote here in purple, 4 to the x. And if we were doing a t-chart for 4 to the x, let's think about how we would set up our x values. So we would choose 0 for the middle, and then -2, -1, 1, and 2. So that's what I'm going to choose for my y values here. Okay, so I'm just going to do this t-chart backwards from what we normally do because, again, a logarithmic is flipped from an exponential. So here's -2, -1, 0, 1, and 2. Now if I put these y values into this exponential here, and if I think what 4 to the -2 is, 4 to the -2 is 1/16, that will give me my x values for the logarithmic. Okay, so this is 1/16. 4 to the -1 is 1/4. 4 to the 0 is 1. 4 to the first is 4, and 4 squared is 16. Okay, so these logarithmics, all it really is taking what we normally do with x first and then getting y and switching that, starting with y and then getting x. Okay, so these are not the values we're going to plot though, because we have to keep in mind, what does this -1 up here mean? Well, this -1 up here means that we're shifting the graph to the right by 1 unit. And when you're shifting the graph to the right, that just adds 1 to each of your x values. So each of these x values here, okay, we're going to take each of those x values and we're going to add 1. The y values, however, are going to stay the same. So the t-chart that I'm going to use is going to have the exact same y values, -2, -1, 0, 1, and 2. But my x values are going to be adding 1 to each. So 1/16 plus 1 is just 1 and 1/16. 1/4 plus 1 is 1 and 1/4. 1 plus 1 is 2. 4 plus 1 is 5. And 16 plus 1 is 17. So these are the values that I'm actually going to plot for this graph. Okay, so when I go to graph these, I also need to keep in mind that my vertical asymptote will have also moved to the right one. So instead of being at x equals 0, your vertical asymptote is going to be at x equals 1. So here's my boundary line for this graph. Okay, so we'll plot 1 and 1/16 -2. That would be about right there. 1 and 1/4 -1. 2, 0. 5, 1. And 17, 2. I'm not going to be able to get on this graph. It's going to be somewhere way over here. So this is what my logarithmic function looks like for this graph. Again, the range is all reals. The domain values are all to the right of our vertical asymptote. They're all x greater than 1. As the y values get larger, x also gets larger. So x approaches infinity, we say. As the y values get smaller, okay, x gets closer and closer to +1. So x approaches 1. Our x-intercept for this graph is here at 2, 0. Okay, let's jump down to number 4 and do the same thing. We have f of x equals log base 3 of x, and then we're subtracting 2. So I'm going to start out by thinking of what the table for f of x equals just log base 3 of x looks like. And again, to start that table, what I'm really doing is I'm starting with my y values, and I'm thinking if it were f of x equals 3 to the x, what would I pick for the x values? The x values, again, would be -2, -1, 0, 1, 2. So that's what I'll choose my y values to be here. 3 to the -2 power is 1/9. So my x value here will be 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. So this is the t-chart for this logarithmic function. Now, what does this -2 here mean? Well, because it's not in parentheses, that -2 is actually my vertical shift, and so it's a shift downward. Okay? If I'm shifting down 2, that's affecting my y values, not my x values. So in this t-chart that I'm about to do, for my actual function, my x values are going to stay exactly the same. It's my y values that are going to be different. It's going to be all the y values and then subtracting 2. So our x values will still be 1/9, 1/3, 1, 3, and 9. Your y values, though, -2 subtract 2 is -4. -1 subtract 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. And 2 minus 2 is 0. So the y values will have changed for this one here. Whenever there's a vertical shift, okay, the vertical asymptote won't change. So because there was no horizontal shift here, our vertical asymptote is going to stay at x equals 0. So we have 1/9 -4, 1/3 -3, 1 -2, 3 -1, and 9, 0. The range will be all reals. The domain x values are all greater than 0. As the y values get larger, x also gets larger. So x approaches infinity. As the y values get smaller, x approaches 0. And our x-intercept for this one is 9, 0. All right, number 5, we have f of x equals log base 1/2 of x plus 9 plus 4. We'll start this out with f of x equals just log base 1/2 of x, and then go from there. Okay, so I'll start out with y values again at -2, -1, 0, 1, and 2. Ask yourself, 1/2 to the -2 power, that's going to give you what? That would be +4. 1/2 to the -1 power, +2. 1/2 to the 0 power is 1. 1/2 to the first is 1/2, and 1/2 squared is 1/4. Okay, so now that I have this table, I'm going to think about my transformations. I have two transformations here. This +9 means that I'm going to be moving my graph left 9 units. So my x values, I'm going to be subtracting 9 from those. And then my +4 here means my graph is also going to be shifting up 4. So I'm going to be taking each of these y values and adding 4. Okay, so both my x and my y values will be changing. 4 minus 9 is -5. 2 minus 9 is -7. 1 minus 9 is -8. 1/2 minus 9. Okay, think about what that would be. That would be -8.5. And then 1/4 minus 9 would be -8.75. Okay, and then my y values, okay, will be adding 4 to each of those. So for your y values, -2 plus 4 is +2. -1 plus 4 is +3. 0 plus 4 is 4. 1 plus 4 is 5. And 2 plus 4 is 6. So this is the table that we'll use to do our graph. Think about your asymptotes. Your asymptotes normally at x equals 0. Because we're going left 9, that's going to put my vertical asymptote at x equals -9, shifting to the left 9 units. So this is where our vertical asymptote would be for this graph. Okay, so we'll plot -5, +2, -7, +3, negative 8, 4, negative 8.5, 5, and negative 8.756. So our graph is going to look like this. Now let's also, before we finish this graph, think about the x-intercept, since I don't have a 0 listed on this t-chart. So if your y value is 0, what would the y value have to have been over here? Well, since you were adding 4 to each of your y values, that means that this would have had to be a negative 4. So what is 1/2 to the negative 4 power? Well, 1/2 to the negative 4 power is going to be 16. Okay, so your x value over here would have been 16. So if you think about this 0.16 negative 4, doing our left 9 and up 4, that would have put the y value at 0, and then 16 minus 9 would have put your x value at 7. Okay, so this graph is actually going to have an x-intercept at 7, 0. And that makes sense based on the way this graph is going. So there's my x-intercept for this one. We'll go ahead and mark that now, 7, 0. Range, all reals. Domain, all the x values that are greater than 0. As y gets, larger here, x approaches negative 9. Okay, x approaches that vertical asymptote at negative 9. And as y gets smaller, x approaches infinity. Okay, number 6, I'm going to have you do those tables and that graph all on your own, and then we will check that when you get to class the next time. So complete number 6 on your own, and that will be what I check the next time you get to class. Until then, have a nice day. You're all wonderful people. Take care.